start. Again, thank you to be here for the lecture of today. Let me, before introducing the topic of today, which is an exercise, but in which I will include some important concept, I hope, let me reconsider very shortly again the test of the observability. I will upload everything in one folder this semester. I didn't distribute for each lecture what I did, because this is YouTube channel, you can see, and then you can switch in the My Study, which we can find one folder with all material which I will which I considered here. It probably something more, no? Because as I told you, I have the electronic version of everything which I'm building now with the student. But I realize that sometimes there is some mismatching, in which sense the students sometimes didn't interpret it correctly some symbols, but it's intuitively to understand what is the error. Let me say the error is not error. It's some letters which has not exactly reflected. Just to understand, you can see here J, and the students sometimes they don't put here J because it's not a student which can understand exactly the topic. No, it's a student which I found for doing this. Okay, let's consider. Please pay attention very shortly to sum up what we did last time. Let me consider this system here, which is the motor which you have seen during the semester. No? Here we have the electrical circuit. The electrical circuit is not exactly correct, because we can see that here we have the feedback, or let me see, the reaction of the mechanical system into the electrical dynamics. But anyway, we can say that the electrical equation, if you want, but electrical equation makes more sense because K multiply omega is the voltage. But in any case, the dynamics which characterize this the current, no? The dynamics of the current. This is correct. The second dynamics or equation reflects the dynamics of the omega, no? In the sense, let me say, the mechanical dynamics. Look, but we have seen in detail this. Assuming that I want to estimate D, which represent the disturbance, the load of which we can see applied. Or I have a motor and I have a disturbance which is in a torque in this form here, which is in a torque. Look, as I told you before, if I want to estimate, I don't remember what I'm measuring. Okay, I am measuring current both, no? Just to understand, just to do an example a little bit more advanced with respect to the last time. Last time we had just one state. Therefore, I told you we have to check just one determinant of the observability matrix. Now, let me a little bit generalize. We have two measurements, current and omega, and I want to estimate again the sense current and omega. Why I can say again, even though, as I told you, the estimation again is not so correctly, because I measure the current and omega, current and velocity, and I estimate current and velocity. Because measurements is measurement, estimation is estimation. The estimation, if the hypothesis of Kalman are guarantees, if hypothesis of Kalman are guarantees, is better than the measurements. Intuitively, just to understand that this is a filter, we filter the noise. Of course, in order to say that is better, must be optimal. Because not necessarily a filtered signal is better than the measured. You can destroy also the information if the filter is too strong. Roughly speaking, just of course, we have a delay, a phase delay. This is not valid in this sense, but in the sense of Kalman, it's valid, assuming that all hypotheses are correct. There is also a theorem, no? Gauss-Markov theorem. I have not in mind if this Markov Gauss or Gauss Markov. But anyway, it's intuitive to understand. Yeah, we measure both, and we want that. Let me assume that we want to estimate current and omega, even though I measure, and the disturbance. The disturbance is in the classical variable to be estimated because as a disturbance typically is not accessible. If you consider that the load can change over time, also randomly, makes sense to say to augment the disturbance exactly in the Gaussian form. I mean, this expression here is, in deterministic sense, extremely strong. Do you remember? I repeat it many times because this means that the disturbance is constant deterministically. But inside the Kalman filter, I can realize in a stochastization using the Q component corresponding to this variable. And in this sense, it becomes possible to be estimated. Do you remember when I introduced the Kalman filter, I introduced also the estimation of R, not this variable. It's exactly this. But concerning what I told you before, if I want to estimate just the load, it's load as an augmented variable, in this augmentation, the system remains linear. Why that? Because the system consisting of this dynamic, and this augmented dynamics, let me say artificial dynamics, because it's our representation, is linear in terms of current, in terms of omega, in terms of d. Now I don't have time to tell you about what is in a linear system, but it's clear what is in the sense that we have just a linear combination of what? Current, omega, and d. Linear combination means I can combine these three variables using constant and so on. No multiplications. I don't know if you remember, but I don't have time to put the definition, even though it's extremely easy. It's the superposition principle. No? I don't know if it's clear. You can see here, but I told you a little bit about linearity, no, just intuitively. I have just here the linear combination. Also the input must be considered because in this case, we have the dynamical system, which depends also on the input. But you can see this linear combination between inputs, the states, and also the augmented state. They are a combination of multiplied by constant and the variable which are considered as the dynamical variable. Again, current, omega, and d. But of course, if I include in my model, because I need, it could be that I need, just an example, to estimate also the inertia of the motor, that the system is augmented. Using this augmentation, we have to verify if the system is linear or not. But in this case here, the system becomes nonlinear. The reason is that J divided current divided U divided D. I would like to say strongly nonlinear, even though strongly is just a feeling. Again, if I have to consider just the system here, I don't need to use this test here. It is enough to use the linear test, which we have seen. In particular, linear time invariant, no? Because the states are three states, and all the rest are assumed to be constant. Okay, but for this system here, I have to use, you remember this, last time I consider in a more easy system in order to show you how calculate O0, O1, O2, and O(n minus 1. Yeah, it was the definition. I don't have time to repeat as we don't need. But in any case, this states and sufficient condition. This means we can give us nevertheless information what I can do in order to obtain the observability. please, this independently how I realize the observer, no? Not only for the Kalman filter. Lundberg observer, do you remember I introduced the Lundberg observer, sliding mode observer. I didn't tell you about the sliding mode observer, Lyapunov Bayes observer. We have many kind of observers. The last time we did exactly this calculation with MATLAB. Do you remember? Very important, and this is something which remains valid in almost all, I would like to say in all augmentation. Do you remember that the derivative of the variable must be not zero? No? Yeah, look at this. What I want to show you. If this is what I measure, look, O0 consists now of an two row instead of one. We have a four state, 1, 2, 3, 4, and two row because I measure two variables. Basically, I do the partial derivative. Do you remember of this field here? Of this, it's not exactly a field properly because here I don't have a differential equation. It is a vector which consists of two variables. The field is this. No? If you look at this expression exactly, this is the field, and this is basically the output. Now, I don't want to be boring again. O scalar F. No? Basically, this matrix scalar. This matrix here, which is basically a vector, which this component, first component, second component, third component, this component. This means this matrix here multiply a vector which consists of this component as first component, second, third one, and fourth. We will obtain, believe me, this here. No? We have here basically O multiply F in a matrix, which is characterized by two row. Here we have in a matrix which is characterized by a column, and we have this result after the gradient for with respect to I, with respect to both. I mean, in order to understand, O multiply F is in a matrix. And then we can do this calculation better with MATLAB, in order to avoid mistakes. S1 is in the long term, which is this expression here. Let me see if I can be a little bit more explicit. Yeah. I can be more explicit because it's basically the result is here. No? Look, O multiply F is characterized by a vector with two rows and one column. This is the first component. This is the second component. Why that? Because this here, this row, multiply the vector characterized by this component, this component, this component, this component as a column. I will take just this element here of the, this is a scalar function which can be characterized, can be written as the derivative of current with respect to time. I can do the same here. I can explain the same way why we have the omega with respect to t, because this row multiply again the fields, which consists again of this, and this, I will get this. Then if I do the gradient of this expression here, I will obtain here. If I do the gradient of this expression here, I will obtain this here. Please, S1 is a little bit complicated because it's the derivative of this expression with respect to J. Excuse me, yeah, respect to J. This is easy, 1 divided J, because it's the derivative of this with respect to D, which is minus 1 divided J. Okay, of course, if you go ahead, the, the calculation is complicated. Therefore, I told you last time the method with MATLAB. And at the end, nevertheless, I have here, as I told you last time, an observation matrix, an observability matrix, better to say, which consists of P rows and column, in which P, as I told you, is the product between the measurements multiplied states, and N is the state. You can see that in this case, you have to check a lot of determinants, because this means, and we have programs in my group which test all possible determinant, because the determinant, to calculate the determinant, the matrix must be squared, meaning, this means we check all possible combination of the paths, which through the measurements, which is not one, I can invert the system. I can get information. Basically, the observability can be trivialized in the sense when if I have a possibility to invert the system, basically from the measurement to reconstruct the state. Just to have a feeling, what is the observability? It's not wrong to say it's the invertibility of the system. If using the measurements, I can reconstruct univocally the state. It's something like an invertibility of the system. And of course, if I have more than one measurement, in the sense of the state measurement, an output, the output is more important than the input, even though in nonlinear systems, as I told you last time, the input plays no role. You remember weak observability, not weak observability. Also last time, the conditions involve the input. Do you remember? U which multiply the insufficient condition, the derivative of the current, in case we want to estimate R and L. And this is a little bit the concept that exists, a possibility to invert the system, to have information from the output, state output, measured, to invert this means to have information from the output of the state. Of course, increase the number of the output, we increase the probability of the observability to obtain an observability test, let me say, positive. No? Or, do you remember last time, we reduce the conditions. And in this sense, let me say, increasing the augmentation, we reduce the possibility. In other sense, because we introduce uncertainties. This is not visible here. But anyway, this aspect, last time we analyzed very well. I didn't tell you about the measurements of the observability, but it's intuitively that's increasing the measurement, the state which I measure, I increase the level of the observability because I include more information intuitively. And increasing the number of augmented state, I reduce. I reduce the level of observability because I introduce in the system something which is stochastic. This means no, let me say, deterministic information. The deterministic information is something physical, is something which is in the system. Here is our model. We think that the variable is random. This means, of course, this is an hypothesis quite, let me say, conservative. Now, with respect to a priori knowledge of disturbance or of the inertia. Okay, I don't know if I forgot to say something, probably yes. Again, if I consider this, the system is linear. This means it's more suitable, I would like to say, to test within linear test, because the linear test is also and it's also a necessary condition. But anyway, you can use also this one, but it's just sufficient. This, no? In any case, we'll be satisfied, no? If the system is observable, as in this case. Okay, I have to call just shortly. In the meantime, I put for you the example which I told you last time, in order to show you, and also with MATLAB, if the nonlinearity is just, here we don't have an augmentation, it's just in a physical nonlinearity. In this sense, let me say, roughly speaking, that to estimate is something easier because we have a nonlinearity which is structured in physical sense. Of course, if I start to augment, what I told you until now remains valid. I need a few 2 minutes and then I will come back. Let me stop the registration. Of course, if I include some parameters, here we don't have, it seems to be, at least I didn't have this, I didn't display, I didn't include parameters, but we will, of course, we will end up in the case which I already presented, which I already discussed. Yeah, I think we can start with this example, in which we can see, that we have let me consider this in a mechanical system, basically. You know, if I consider x1 as the position, x2 is the velocity, because the derivative of the position equals the velocity. And this equation here states, yeah, the dynamics exactly. This is a kinematic condition. This means x2, as I told you, could be interpreted as a velocity. This means x2 derivative is the acceleration. This means this expression here can be considered as a force divided mass, which is equal to 1 in our case. This is an artificial example to show you the Kalman filter. I will show you the software. And again, today I try to upload all software. The software will be not in one folder for each lecture, but I will upload the material, the manuscript in a unique folder at the end, something like manuscript or something like that, no? Of all lectures. But the software will be associated to the lecture, to the corresponding lectures. Because sometimes, you remember, I use the presentations and so on. Okay. Look, try to analyze this equation here. Again, this could be considered as a force. And all these elements represent, let me start with this. It is more complicated. This is could be interpreted as a Coulomb friction force, like in the sense, yeah, it's a Coulomb friction force, but it's a particular Coulomb friction force, which I am considering just the yeah, the odd, the even the component of the Coulomb friction force. I mean, typically we have also not only the even, but the odd component. What I intend, this element here is the static friction, because the static friction is a constant multiplied by the sign of x2. X2 is the velocity. This means the friction, think about the model, is always against the movement. This means against the velocity. X2 is the velocity in both directions. In this direction, if this is the positive, we have a minus. And in this direction, which is negative, we have a plus. This means it's always against the movement, this friction component. Typically, we have also a linear component. This means we have to add here minus x2, which I didn't put. I don't know why. Therefore, like. I don't need to multiply the SGN x2 because SGN is an odd function. This means it's always against the movement. No? I mean, the friction is always against the movement. And this is characterized if I consider the Coulomb model of the friction by the function SGN, which is defined here, which must be multiplied by the even component of this model. About the friction, I'm not expert, but I am using the friction models in the context of my work with the system theoretical or control systems. As I told you probably many times that in friction is in a field. The name of the field is tribology. If you look, tribology, we have many chairs at the university. Tribology is the analysis of the friction. Just on this topic here, which consists of lubrification methods in mechanical fields. This means I'm not so expert, but my life I worked with different model of friction. Yes, the name is Coulomb friction because it's not dynamics, because in a polynomial, let me say, in a polynomial approximation of this complex phenomenon. Now I'm working in a bachelor thesis with a student, and in which we are analyzing. I work also in Aditrans with this topic, in a project of this topic, the control of the slip of the wheel is this one. Of course, we cannot change the friction, or at the least we cannot change the friction between wheel and the surface in which I am rolling, but we can put some conditions about the velocity in order to reduce or increase the friction. Depends what we have to do. It's the ABS system in the brake phase. This I work also in Volkswagen, this topic here. The idea is to brake the car without slipping, in order to have, nevertheless, the control of the car. I don't know if you know ABS system. It's a complex problem. It's a complex problem. But if you consider just this example here, the Kalman filter plays a role in this project here. This we can see from here, not everything depends on x2. X2 is the velocity. Also in this model here, we have also more complex model, Lou-Gray model, in which we have a dynamical Lou-Gray. Lund-Grenoble. It was in a project was the model investigated by University Lund and Grenoble in France. Lou-Gray model. You know that? Lou, G-R-E-E in English. G-R-E-E. Lou-Gray, the gray because came from Grenoble. In English, probably Lou-Gray, you can say, but somebody pronounced Lou-Gray because it's Grenoble. No, this in France. Did you find it? Lou-Gray friction model. Okay. Yeah, Lou-Gray. No? Or if you want Lou-Gray, you can pronounce as you want. A Coulomb friction model, did you find? No? It's a polynomial. It's a static model, but nevertheless useful for projects. Again, just a few words. The friction is an extremely important component in the mechanical system because it's not always something which we have to be considered negative. In the brake phase, but not only in acceleration phase, if the friction is zero, you don't start. You remain where it is. If you walk in the frozen road, the stability is not clear. This means it's not negative. Everything in our life, positive aspect is negative aspect. Depends. Anyway, let me go ahead now after this consideration. SGN is clear what is SGN function. It's a sigmoid function. Probably data science students know very well when it's sigmoid function here, which in the context of control, we used many times. very often to stabilize the system, for instance, in the sliding mode control, we introduce in using the controller and a friction, an artificial friction, again, in order to stabilize, in order to limit the output. Of course, it's an artificial friction in the sense it's not a physical, it's not as a physical friction, like in the sense, but it's something which the controller introduce with the same effect in order to brake, in order to stabilize. Anyway, look at this function here. It's the ideal, let me say, yeah, I don't know if I can say so, but in any case, sigmoid function means recall the S. But look, it's a function which is not continuous. In this sense, this model here is, of course, is an ideal model, because you can see that the force, the friction force, yeah, could be better to write FR, but it's exactly here defined, which is this here. If I consider this mathematically, we have a force which is not continuous. Now, physically, I'm not a good physics, but I don't know if this is really a valid model. This means very often we approximate this function here with an hyperbolic tangent, which changes between 1 and -1, or 2 divided by arctangent. But of course, in order to approximate, I need to increase the argument. Let me see if I have something here to explain what I intend. I mean, this dashed line, which try to approximate, we have this dashed line on the continuous line, we try to approximate, let me say, better and better this ideal function, which I would like to say does not reflect the physical system, because I can imagine that the physical system, or the friction, the physical system really doesn't change rapidly. It seems to me, I'm not expert, but typically we approximate also this Coulombian friction with a continuous function. This could be, for instance, as I told you, arctan or arctg, I don't know which kind of notation you like. Here I put x2, I didn't put, but 8x2. No? And with this gamma, is a constant, larger and larger gamma realize in a better and better approximation. I don't know if you remember math, but nevertheless continuous, because we assume that we have a continuity, even though the change, in accordance with my experience, it seems to be, from the literature too, an abrupt changes, but continuous. I mean, what states this? States basically the effect of this abrupt change of the static friction. It seems that I have to overcome an initial force in order to move. But this is just the feeling. Probably I am moving also in an not perceiving form, because in the literature, we find really this approximation as if the phenomenon is nevertheless continuous. But of course, we don't perceive, probably. We tend to model in this sense here. But of course, probably it's in physically, we have a continuity. But let me go ahead. Let me consider this mathematical, as I told you last time, the mathematical expression. Because nevertheless, we have advantage and drawback considering this idealization. Physically, I would like to tend to approximate the phenomenon in continuous form. Jacobian. F1 is the first component of field F. No? Do you remember the field F consists of two components and a vector field of two components. This first component, second component, I called F1 with the first component of the field F. No? Do you remember in our typical notation, F include both the derivative of partial derivative of F1 with respect to x1 and then the partial derivative of f1 respect to x2, and again, partial derivative of f2 respect to x1, and the derivative of f2 with respect to x2. Calculated, we can see here, at the previous, previous that means corrected, no? Previous x1, x2, and the actual u. Delayed. This means yeah, I am assuming that I am using forward Euler. Otherwise, I have a UK, assuming that I can explicit UK, because I don't know if you remember, I told you about a little bit about the implicit and explicit method, even though I don't have time to told you about that. And I don't think so. We will see later if I have time a little bit to tell you about backward Euler, which is an implicit method. In a linear case, could be a problem to obtain an explicit model, which we use in Kalman, which we need in Kalman. Let me go ahead. In this sentence, I hope to improve using an easy example. As long as the system is linear, no problem. But here I don't see problem because in a particular non-linear system, but it could happen that the system, if I use an implicit method, for instance, we have in the Runge-Kutta, in backward Euler, which have some advantages, but the drawback that the discretization could be a problem in the sense of explicit form. I come back shortly today on this topic, but to understand, I have to do an exercise. But let me go ahead. If I do the discretization of this system here using forward Euler, very important to say which kind of discretization I am using. We had a project with Rolls-Royce in which we used backward Euler. First of all, why backward Euler and not forward? Also, without showing you the backward Euler is difficult to understand, but the system or some technical aspect called for backward because backward had more stability, let me say, characteristics. But of course, I have the drawbacks to obtain an explicit method, an explicit mode. I told you about explicit exactly now. With this hypothesis, I have a forward Euler-Kalman filter. Please notice how the discretization characterizes the Kalman filter, because the Kalman filter, you have to be careful if you have a different discretization, because change a lot, I would like to say, in Kalman. We don't have time really to go in depth on this, but if you want, we use in some project, we can go a little bit more in depth. Look, if I replace, we have seen many times, if I plug in this together with the input u of t equals uk minus 1, I did input here because it's trivial. I did input here, but u of t equals u of k minus 1 in the context of forward Euler. In the context of backward, this does not change, but change, of course, yeah, I did input also, yeah, excuse me, in backward, here I did input u, if you want, I can write. So we have everything. In forward, this is the definition, which means to consider k minus 1 as the actual value. In backward, the derivative does not, or the form of the derivative does not change. What I intend is the actual value. I intend x1 of t and x2 of t, x1 of k and x2 of k, and u of t equal u of k. This means as if I look back. Here, I look forward to analyze or to describe the dynamics, which is represented by the derivative. Dynamics is movement, dynamics is changes. If k minus 1 represent the actual value, look here, to approximate the dynamic, I look forward, because this is the future with respect to the present. If I consider the present x1 of t, x2 of t equal x1 of k equal x2 of k, and also u of t equal u of k, I approximate the dynamics, the variation, looking back, just to give a feeling. This changes a lot in the model. Let me go ahead because I would like to show you also the simulation. Believe me, if I do the calculation, plug it in directly without thinking, I will obtain this one. Of course, we can see that we could have some problems if I have here instead of k minus 1, if I have a k. If I have a k, no problem in this sense here, because I have a k minus 1 saved, but I measure uk. This means in this form here, in terms of backward, I don't have problem in this form here with respect to u. But here, look, if I have a x2 of k is 2 of k, the explicit form of the model which I need to state the dynamics in Kalman is not easy. I mean, we have something which depends on itself. It's not explicit, it's implicit. We can do, but we have to do some approximation or method in this implicit form. It is a little bit complicated. The advantage, this is the price which we have to pay. The advantage is inside the structure of backward, or the implicit, which typically is more stable, but we need an explicit form to be implemented in Kalman, which typically more stable means to use a little bit larger, I would like to say, simple time. And this technically is useful because the Kalman filter, as the control system, run both inside the sample time. I mean, the value which I will calculate is calculated microcontroller inside the sample time. This means if I realize the control system with an observation, with an observer, and everything is complex because I'm using model predictive control or different complex Kalman filter itself, cost computation time, cost calculation time, we need time. It could be an advantage to have a larger TS. This is one of the advantages, but not the unique one. In order to be able to calculate what I need without risking, or with less risk in case of nonlinear, to have an unstable system. Again, for linear system, we say that the backward Euler is an A matrix, or the A matrix stable dynamics. This means starting from a stable continuous system with backward, we have a stable system independent of TS. In nonlinear, this is not valid anymore, but more stable than forward. Okay, the calculations are easy. The derivative of f1 with respect to x1 is 1. You can see from here. The derivative of f1 is this component here. The derivative of f1 with respect to x2 is ts, excuse me. Sometimes I call t, sometimes ts. Look at the derivative, the gradient of this equation here. We have 2 times ts. If I consider this equation here with respect to x1, why that? Because x1 appear linearly, and I have to multiply by ts, minus 2ts. I don't know if it's clear, this derivative is partial derivative. The partial, or the derivative of this line, of this component with respect to x2, it is here. I would like to spend a few words here, and then we will see together the software. Here is something a little bit critical. I told you also last time quickly, because the derivative of this expression with respect to x2, this is no problem. 1. The derivative of this component with respect to x2 is 1. Please pay attention to the exact definition. The derivative of something which depends on k with respect to something, the same in this case, or something, let me say in general, with depends of k minus 1. This is a little bit the necessity, not only here, first of all, to have the prediction. If I have x2 of k with depends of x2 of k, we cannot speak about the prediction. I mean, here is the present as a function of the past. This is the prediction. Or if you want, future as the past, so of the present. You can interpret as you want, because it works for each k. The prediction needs that on the left part, we have a k, let me say, on the right part, you have a k minus 1. Or if you want, k plus 1 and k here to predict in the prediction phase of the model. Of course, if it's not the case, if the system is implicit, thus k appears also here in terms of states, of course. We cannot speak about the prediction because we have a k here and k here as in backward. But we need the prediction also to apply this form of the Jacobian, because the derivative of x1 of k with respect to k minus 1. This means must be in this form. Otherwise, I have to do something different. We have a different Kalman filter. We have an uncentered Kalman filter, which we don't use the Jacobian. I don't have time to tell about this. But at the end of this course, you have the possibility to interpret, to go ahead with different Kalman filters. Uncentered Kalman filter, one of them in the family of Gaussian white noise Kalman filter. But you have many other Kalman filters related to not Gaussian white, but really, this is a really more advanced thing. Again, on this component here. Here, I assumed, or better to say, I didn't consider the derivative. Do you remember last time I told you? The derivative of this component, yeah? At x2 equals 0. Now, can I do that? Why I did so? I did so, first of all, because Sgn of x2, mathematically, I cannot do the derivative for x2 equals 0. Because x2 equals 0, we have a not continuous function. This means, you remember math, we defined the left derivative, right derivative, but left and right derivative is 0. But what happened at x2 equals 0? At least in terms of the derivative, it's not defined. No, we learned in the high school. If the function is not continuous, we cannot do the derivative. Or we extend x2 at time 0 minus, x2 at time 0 plus, left and right. Here, left and right is 0. The information which I can say that left and right is 0, and what happened at 0? Undetermined. This means I cannot write. If it's not determined, I cannot try explicitly what is. This means it's not totally wrong what I say, because it's, I don't know. But the Kalman filter, when x2 is close to 0, it could be that realize something which is not. If I use exactly this model with SGN, of course, if I use the model with the approximation, arctangent or hyperbolic tangent, I can do that. But of course, the expression will blow up. Calculation increases. We will see that very often could be, nevertheless, could be. It's what I can do. Because I cannot write something which is undetermined. Nevertheless, the error which I have for x2 equals 0, because could represent a problem, can be compensated, you remember, with this variance on the model somehow, because this model here is still something abstract. It's still something which does not represent exactly the physical system. This means if you remember the equation B of the Kalman filter, in which we have the a priori estimation of the covariance matrix, P minus we call it, equals Jacobian transposed, multiply P k minus 1, a posteriori covariance matrix, multiply J Jacobian plus Q, this Q try nevertheless to include also what is wrong in the Jacobian, if something's wrong. Yeah. Yeah, it's just everything written in vectorial form. Let me show you the Kalman filter in MATLAB to conclude. Next week, I will start with some variation of Kalman filters, but always inside this kind of Kalman filter, extended Kalman filter, in the context of Gaussian white noise. No? We have two streaming in this context, unscented Kalman filter and the extended Kalman filter with the hypothesis Gaussian white noise. The unscented Kalman filter, I don't have time to tell because it's a little bit more, I don't want to say complicated, but calculations a little bit heavy, really, because he considered more points in the linearization. And then, let me say, sum up or consider in a weighted mean value, something like that. No? Sigmoid points is the point in which we linearize the system, which is not one as an extended, but more than one. How many? This is an open problem, I hope so. Okay, let me open MATLAB. So I show you how work this, and next week we will try to attack some kind of Kalman filter, cascaded and so on. And nevertheless, I will tell you about a little bit, how possible to say, the Kalman filter realized in output Kalman filter, because H could be a complex function too. And it could be that I will tell you about backward and so on. Let me open MATLAB. About the material, because some student ask me about the material, I will take care, and then we will see together, starting from next week or after next week, how the material my study is organized. No, so I show you. But very important for the project, also per Zoom, keep in touch with me, because this is a seminar. We don't have a classical examination, which we have to come here to in German Klausur. No? It's the project. This means the contact with me per Zoom. Also, it is important to fix up some first of all the topic, and then during the process to realize the software, you will see that we have some possible some question and so on. Very important to download the software which I will upload, or I give you extra software depending of the project which you. Okay, MATLAB. No, I am stupid now. Let me open this one. It's a shame, old. I need 10 minutes, but in any case, I have to recover because of I started a little bit later. I hope that for you, no problems. I will share now MATLAB. Is it difficult, Kalman filter? Yes, a little bit.
Not much background knowledge about people,
But did you hear about Kalman? Yeah, of course. Did you hear before? No.
No.
But if you look in Google, put any kind of applications, which of course we need dynamical systems, we need to identify, is present almost every. Try to, I don't know, climate changes, Kalman filter, or I don't know, in technical fields, we applied in Volkswagen almost everywhere, in cruise control, in position control. Position means auto parking. I work in ABB Research Center in Heidelberg, was presented I don't want to almost in every project, but yeah, many projects can be integrated with knowledge in data science. Yes, to identify QR. We do also here. We do. We use not directly neural networks, but methods, PSO, particle swarm optimization methods. Probably you heard about that. To be able to fix this element, which really is the main problem of Kalman filter. I met once Kalman, I already told you that, in a conference, and the professor asked him in challenging form when Kalman filter does not work, but it seems to be that it solves many problems. He looked at, I repeated to my student many times that Kalman filter cannot work. And then, of course, the question was challenging, the answer in the same way challenging. And then he clarified that we cannot work mathematically because we cannot, also in a linear case. In the nonlinear, we have not convex optimization problem. This means no guarantees. No? We have to be close, as I explained, to the result of the convexity of the region of the convexity of the optimization problem, which is the function to be optimized, this a posteriori, error covariance, and so on. The trace, and then each element is guaranteed in linear case. But we can use method to estimate Q and R. But of course, we hope the answer was perfect. Cannot work. If work means we find the optimal and the convergence. No? Now, in linear case, but also the linearity is an assumption. What is linear? It's an abstraction. Does not exist probably real in a linear system. This means cannot work. But of course, we can approximate, and with this knowledge in data science, we can also estimate in ABB. I remember that we have routines using neural network or also PSO to estimate Q are a little bit easier to do. And to estimate the initial value of the error, this means to estimate the state. And then when we start with the observer, we hope and then we are able to say that we are relatively close to the optimum or one optimum. It could be more than one, and then not convex. And then at least we will converge somewhere. And somewhere. Somewhere. Okay, let me now try to open the file. Let me share. Let me see if I find now the folder. It's running. Let me look at the integrate camera. I think the Simulink. Yeah, it's running Simulink. 1 second. Did you find many information about Kalman? A lot of them. But in accordance with my experience, really is it's important algorithm for, at least in engineering fields, in data science, in applied mathematics. We have here a project also in medical systems. I can show you in paper in which we try to estimate some, for instance, sugar, this in the blood, or some hormones. I show you what I intend, so more clearly. Okay, let me now share Simulink. Yeah, look. It's not so very well organized software, but I hope it's understandable. Look, what we have here is exactly the model which I presented. This means we have u, we have here the derivative of x2. After the integral, we have x2. After the integral of x2, we have x1, because the derivative of x1 is equal to 2. And the derivative of x2, which is here, is u minus 2 times x1. I don't know if you remember last time I told you the x1 or 2 times x1 could be interpreted today, I forgot to say, as a reaction of the spring, and the linear spring. And the linear spring. Of course, about the spring, we can do similar consideration with the friction. If the spring is not linear, we have to approximate its characteristics. I mean, it could be that in the central phase, I mean, when the spring is really compressed, I can imagine that the force as a function of the position is not linear. I cannot compress in the linear phase when I am in the final part of the compression. I can understand. This means also this could be considered as, for instance, in a polynomial approximation. For instance, this is basically our system consists of a spring. Our system maintains this. The physical system consists, we can say U and the force divided the mass, which is 1 in this case. We have two antagonist forces. And the friction, as I told you a lot. And this here, again, antagonist. But this is antagonist with respect to the positions. Could be considered in a spring, in a linear spring, because the spring reacts linearly. At least this is the model. No, God knows what happens, but this is a possible model which could be somehow validated. Just to show you, even though the system, the example is artificial with these values, but conceptually it could be interpreted as let me say in a real case, at least in its component. Of course, the value is didactical value, because otherwise I have to write really something strange. The parameters can be identified. We do that. How? Augmentation. Look, this is clear. What is this? This is exactly the Coulombian expression. We can see here that we have x squared. You remember x2 squared plus 1. This is the static friction, minus in any case. And both 1 and this square, all even function, are multiplied by this sign. Should I come back to the model, or is clear? Again, these two elements realize x squared plus 1. If I multiply both by sign, and then I put minus, I have exactly this, let me say, complicated things. If you put in evidence SGN of x2, this is x2, from here and here, we have minus x2 squared minus 1, everything which multiplies sine of x2. It's clear, no? It's exactly what I did in MATLAB, in Simulink MATLAB in this sense. I mean, in this phase, in this part, I try to explain the model. No? Of course, you can see, you can try at home that I tried, we can see I tried to replace this element here. This is multiplied by x2, no? S of SGN of x2. This is the argument of this block here. Block is the function. But I can replace, I can throw away this. I can replace with hyperbolic tangent. If you want, you can use 2 divided by arctangent of what? Gamma, do you remember? Multiply x2. Gamma is here. Typically, this is a large value. Yeah, you can see. How means large? Infinite, I will collapse this in the SGN. But you can test at home. You can test at home that no visible difference between. Okay, let me look the Kalman filter very quickly, and then we will run a couple times, and we are ready. This means I have to define TS, because 1 divided Z, we need 1 divided Z. Here I use in an embedded function and not in interpreted. I told you at the beginning I start with interpreted in order to show you this recursivity of the Kalman filter. Here I explain the embedded, which is more comfortable when we have to really to apply in the microcontroller. But basically the Kalman filter is the same. Yeah, we measured here. Let me see what in this example we measure the position, but the system is also observable thanks to X1, the presence of the spring, measuring X2. Why that? Conceptually is easy. You can do at home. Even if I measure X2, nevertheless, thanks to the presence of the spring, the information comes in X2 directly. Indirectly, I would like to say also from the information from X1, because we have a feedback. I mean, it's not necessary to obtain the observability to measure X1, which is at the end of the chain of the system. X1 collect all information. Look, the energy is passing through these two integration, and let me say end up, if you want, in X1. But if I measure X2, it seems that I don't have information about X1, but I have it, thanks to the spring. Therefore, in some actuators, we introduce the spring if we have some system or something which realizes the feedback in the system in order to obtain the observability. I mean, without the spring, if I measure X2, I cannot have information about X1 because we don't have feedback in the system. Do you remember the concept of observability? Feedback to get information everywhere. Let me show you the Kalman, and I run. The Kalman is always the same. This means in your project, this is an indication. Take my software and modify my software. Dimension of the matrix, Jacobian must be changed. We have to change the prediction. Of course, the model is different. But if you remember last time, what I told you or before last time, we can see here, the structure does not change. Of course, I check here, some student ask me to check with different value of Q, but notice that the second equation is quite not precise, because I don't know what I put here, but the SGN, of course, is the function which could be a problem. Already I told you about the problem which you have in the Jacobian. Here I copied here exactly what I told you at the end. I told you very shortly. Excuse me. It's copied. This. Of course, copy in the sense you have to organize the variable in the right way, using in this form. You remember I told you a lot about the embedded structure, considering this if empty, because the initial condition is not outside but is inside, and so on. You have to put this persistent in order to realize the recursivity inside, but the rest is basically copied. Look here. Look what the Jacobian. I copied what I clarified. Basically, of course, copy in the sense you have to be able to change the name, assign, and with the same notation. The rest of the Kalman does not change, absolutely. If the nonlinearity is in the state, we will see at the end of the course if the nonlinearity is also in the output. We have to be, but it's not a problem. Of course, if I have this system here, and I have 3 states, I have to consider instead of identity matrix 2, identity matrix 3, I have to be careful about the dimension. Let me show you the simulation in 1 minute, and we will conclude. Now, I don't remember exactly the value of TS, but I can try. Because this also is a big problem, TS. Should be not so small, should be not so large. I told you why. Because too small, it seems to be a good approximation, but we lose the observability. You remember this concept? I told you because I recall because it's important. Should be not too large because otherwise there is information. Shannon theorem and so on. I don't know if you remember. There is an optimal value? Probably yes. Could be considered an extended TS in order to, this is a big problem, but could be a project for you. If TS is very small, theoretically infinite small, we destroy the dynamics because we have x1 of k equals 1 of k minus 1. x2 of k equals x2 of k minus 1. No dynamics, no Kalman filter, no observer. Cannot be extremely small. Even though it seems to be extremely small, I approximate better. But statically, the signal can be approximated, signals, but not dynamically. I mean, I cannot use the observer. Because please pay attention, the observability, what all our considerations are done on our representation. Because God knows what is the reality. We have just a representation. And then the observability, everything which I can do is just on our, how we figure out the system, how we model the system. The rest, God knows. We cannot be able to really say what happens in the system. But you have a representation. Therefore, again, the test on the observability is on the representation of the system. Okay, now where I am? Oh, 1 second to start the simulation. Where is Simulink? Okay, here should be. Here we have in the embedded, and now we have in Simulink. Let me see if I don't have mistakes. It could happen mistake because sometimes I change something in the last part of the lecture because the student asked me, because I hold this course in identification and a technical university, in which I have more time, I have 2 blocks per week. And the students, the course is not a complementary student. I mean, this for engineers, this means I have the possibility to go a little bit faster to tell a little bit more. No? Here's the course for everybody, must be so. Okay, let me see. I am measuring the x1. Let me see how it is estimated x2. And the rest you can do. That is x2. I don't know if I share. Probably no. I don't remember. Yeah, I shared. The last things, here x2. No? We can see. x2 from the system, the real system. x2, the second variable from the estimation. Let me see if I have some results. Yeah, seems to be. Try to do atom to change the noise. Yeah, we can see that at the beginning I simulated an error, and then we can see we Kalman estimate very quickly or relatively quickly. We don't have augmentation. Try to do an augmentation. How? 1 second, really, I'm finishing. This value is 2. We will see next week, not in this case, in another case. And then I will introduce another interesting variation. If you here put, if I have a 2, but I don't know 2, this means I will augment within a parameter here, like R, like the derivative of R equals 0, and then try to estimate the parameter 2. You will realize that we don't have a system so, let me say, fast, because the level of observability, the system change, let me explain with feeling, change the other one, it could happen that it's not observable. Because if you consider, in this case, will be absolutely observed, absolutely we cannot say, but I suppose, because I measure x2, this means I have close to something which change over time. But if I don't know this parameter here, and I have to estimate, of course, I have a system with 3 states. I have a not convex optimization problem. You will realize, in my opinion, will work, but will be slower, or increasing the Q somewhere, increasing the uncertainty, will accelerate the approximation, but with larger variance, because I will increase, let me say, the a priori knowledge, because if I don't know this parameter, of course, the Q related to this equation, the Q related to the last equation, which must be considered because the hypothesis of the Gaussianity implies the Q, can help in any case to estimate faster, but with a larger variance. This means the mean value will converge, I hope, but of course with more uncertainties. So, okay, let me conclude. Ready? We are ready. Let me stop recording. Thank you for your attention. I am here for question.